we are going to talk about something called end behavior of a function. So if you think of a function and its graph, we are interested in what the function does very far out, away from the origin, or at the, quote, end. And so to make it a little bit more precise, we're going to come up with a new notation for studying what a function does at the end. So on the right side, we will write limit x approaches infinity of the function. On the left side, the value of x is going very far out to the negative side, so we'll write limit x goes to negative infinity of the function. These types of limits are called limits at infinity. Now, I have a little bit of a problem with that. You can never actually get closer to infinity. Infinity is this idea of unbounded, larger and larger and larger, so it doesn't make sense to say that you are going to get to infinity, nor does it make sense to say you're approaching it. You can never get closer to infinity. So in this first part of the discussion, I'm going to talk a little bit about examples using graphs, just so that you can see how we write things, what to expect, and how to analyze them. So we're going to start with the simplest function here first. We'll say the limit as x goes to infinity of just the regular old function x, the line y equals x. In this case, we're asking, what does the function do when I go really far out to the right? The function just keeps going up and up and up and up. So what we will write is that this thing equals infinity. This limit does not exist. The value grows without bound. It does not exist. That's really important. Another important idea here is that there is no vertical asymptote here. Before we said that if you have a limit of a function and it goes to infinity, you have a vertical asymptote. And now you're telling me that we don't. And I think the easiest way for me to say it is that there is no brick wall here. If you've got a vertical asymptote, you are taking the limit as x approaches some finite value. That means you can get closer to it. And if you have that situation where you can get closer to a function and it just goes up, 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 then you've got a vertical asymptote. But here, we don't get closer to any location. And that means we don't have the brick wall. And so there is no vertical asymptote. Now, certain limits we are going to study not by using the limit laws, but by using analysis. So as an example of another limit, we're going to take x approaches infinity of x cubed minus x. If I sneak a peek here, so if I just kind of look ahead and think about what's happening, when x gets really big, its cube gets really big, and at the same time, the other one gets really big. When you sneak a peek and you see infinities everywhere, you cannot use the limit laws. The limits don't exist. So instead, what you're going to do is some sort of analysis here. What we're trying to do is exploit the fact that the functions get big in size. So I'm going to factor out an x and try to write it as a product. And if I keep doing that, I'll have an x, x plus 1, x minus 1. Now I'm ready to talk about its end behavior. What happens when x gets really big? So when x gets really big, this term gets really big. X plus 1 also gets really big. And x minus 1, this term gets really, really big. Think of it as you won the lottery and you were walking down the street and you dropped a loonie. Would you still be rich? Yeah, you would be. So that means together you have an x times an x plus 1 times an x minus 1. They go to really big times really big times really big, which is just really big. So we would write that this limit just goes to infinity. So in some cases when we can do algebra, we should do it. But not all cases work the same. So for example here, if I were to talk about the limit of cosine of x, this limit says go really far out to the right. So as I go far out to the right, the height does not get closer to any value. Cosine just bounces up and down between 1 and negative 1, 1 and negative 1, 1 and negative 1. It doesn't get closer to any value. And since you don't get closer to any value, the limit does not exist. So what we do is we say that the limit as x approaches infinity of cosine of x does not exist. You don't get closer to any value. Therefore, the limit cannot exist. That was one of the terms in our definition of a limit. Now, another function that's going to start adding some important features for us is e to the x. On the right side over here, as I walk further and further out to the right, the function just grows and grows and grows without bounds. So the limit as x approaches infinity of this function is infinity. The limit does not exist. There is no vertical asymptote. The other side is where some interesting stuff happens. As I go further and further out to the left, limit as x goes to negative infinity of e to the x, the height of the function gets lower and lower and lower, but more importantly, goes closer and closer and closer to 0. So we say that this limit equals 0 because the height gets closer to 0 as x goes out to a negative infinity. And so that kind of behavior should be familiar. You say, oh, I know what that thing is. We define a horizontal asymptote, and we'll just call it HA. If you ever have a function where if you take the limit to one side or if you take the limit to the other side, if it equals L, then we say that y equals L is the equation of this horizontal asymptote. This kind of ties up nicely our end behavior discussion. We are interested in figuring out what functions do when I go very, very far out. Some functions have no horizontal asymptotes, and we already talked about that, f of x equals x, because when I go out to the right, either one of those limits just goes to infinity. Some functions have one horizontal asymptote. We just talked about f of x equals e to the x. This function has one right here. And the reason it has one is because the limit as I go to negative infinity gets closer and closer to some number. But there are also some functions that have more than one. Some functions have two horizontal asymptotes. You say, what? How can a function have two horizontal asymptotes? This function is called the inverse tangent function. It's like taking the tangent function and kind of flipping it along the line y equals x. On one side it looks like this, and on the other side it looks like this. The limit as x approaches infinity of the inverse tangent is pi over 2. And if you think about the graph of tangent, you could understand why it has to be at pi over 2. On the other side, the limit as x goes to negative infinity of inverse tangent is negative pi over 2. So we say that over here, the horizontal asymptote is the equation y equals pi over 2, but only when x goes out really far. And on the other side, the horizontal asymptote is negative pi over 2, but only when x goes out far to the other side. And so that kind of wraps up our intro discussion about end behavior. In the next video, we're going to take a look at how to actually calculate the equation of any horizontal asymptotes, not by graphs, but by using calculations.